So continuing on a little bit about on the idea whether spin is not just some mathematical maybe, but actually physical. Well, when I was saying people suspected that there might be something like spin for electrons due to the splitting of spectral lines in a magnetic field. And two of the main guys who proposed that fairly concretely in 1929, Goudsmit and Uhlenbeck, I think they were Dutch. Goudsmit, Goldsmith in Dutch. Yeah, I speak French, German and Dutch as as European languages because I lived in Europe for decades, in Brussels, so I speak Dutch. Uhlenbeck sounds more German. Yeah, I'm not sure. Anyway, these two were young physicists. They teamed up and they proposed in '29 that the splitting of the spectral lines in a magnetic field was due to the electrons having spin. Okay. And then Dirac, the famous Dirac, Paul Dirac, a British theoretical physicist. A lot of people rank him as number 2, and only after Newton as the best British theoretical physicist that there's ever been. He's famous for lots of things, but his equation, equivalent to the Schrödinger equation, but the Dirac equation, and what's characteristic of the Dirac equation is it tries to wed, merge quantum mechanics with special relativity. In other words, he tried to take Schrödinger's equation, more or less, and to make it relativistic. Now, we don't have enough knowledge yet. I'll throw the term at you, the technical term, so you may appreciate the significance of it later when you have more knowledge. He wanted to make quantum mechanics, the quantum mechanical equations, like Schrödinger's equation and so forth, so-called relativistically invariant. I won't go into what that means. It'll become clear the next course, the third course, undergrad course, that I'll be teaching as part of this dozen or so undergrad courses, which are just preliminary courses, support courses for the M1, first year master's level courses. So the third one will be on, it'll be a computer theory type course on theory of computation. The fourth one will be on special relativity. So by the end of that fourth course on special relativity, you'll understand what's meant by the term relativistically invariant. And what Dirac tried to do was to make the equations of quantum mechanics, particularly the Schrödinger equation, the most famous, relativistically invariant. So in other words, the quantum mechanical equation would be consistent with the demands of special relativity. So in effect, he wanted to take non-relativistic, non-special relativity, where the speeds are much smaller than the speed of light and the masses don't increase due to speed. So that type of non-relativistic quantum mechanics, which is what Schrödinger was dealing with, but he wanted to extend, in a sense, quantum mechanics to very high speeds and speed of light and that kind of thing. He wanted to create a marriage between special relativity and quantum mechanics. Well, he succeeded spectacularly, and I'll be giving you several graduate level, M1 and M2 level courses at least, on relativistic quantum mechanics. And I'll be talking a little in a moment about some of the books. I'll be showing you some of the books that I'll be using. But anyway, what's really interesting with the Dirac equation, this wedding of special relativity and quantum mechanics that came out from his work, was the idea of spin. It just fell out naturally from his mathematics, from his equation. Specifically, he got values of the angular momentum from his equation that could take half integer values. So the notion of spin was just a natural part of Dirac's equation. So people began to think of spin as perhaps some kind of special relativity or relativistic effect of quantum mechanics. So that idea got going. Now, just as it is. So this led to thinking that spin is a relativistic effect, something to do with relativity. Okay. Now, it's not just electrons that have spin half. The proton, P plus, also has half integer spin, and the neutrino, zero, just no charge. Sorry, the neutron, and neutrinos, like what are neutrinos? Will I wait to the elementary particles course? They are also neutral, very small. That's why the ino just means small in Italian, like baby. Okay, and these all have spin half. But other particles, for example, the famous capital omega minus, there's a whole story behind that, famous one. I'll tell it to you in just a minute because it's fascinating. But it has spin 3 halves. So again, half integer spin, and interestingly different from these ones that have spin a half. And this omega minus has a spin of 3 halves. Right? Now, not well, perhaps if I get into this, I'll forget about the story behind this. Where do I start on that? How about Mendeleev, the Russian physicist, or chemist, I guess, who classified the elements. He made tables, the Mendeleev table, where he made columns and rows of elements with similar properties, like metals or gases or not inert gases, and he noticed these patterns in the properties, the chemical properties of these elements, and made tables of it. And he noticed that there were such regularities, he could even predict that there were some gaps in the table. So he said to the experimental chemists, look, at this particular atomic weight there's an element missing that's not known to science, so go and find it, and it should have the following properties. So the patterns he found in his chemical table were, inspiring enough, accurate enough, that he was able to extrapolate. He could read between the lines, so to speak, and predict the properties of the missing, the holes, the missing elements, because the consistent patterns. He would interpolate the properties, the numerical values of the properties, like the atomic weight and what kind of properties it should have, because it should be a particular kind of atom, similar to the others in the same column or row or whatever. Right? Well, a century later, pretty much, slightly later, middle 20th century, an American theoretical physicist, Nobel winner, Murray Gell-Mann. I've met him actually. I've spoken with him for, I don't know, maybe half an hour even. He must be early 90s now. One of the he's either the or the second most brilliant man I've ever met. I read that Sir Roger Penrose has an IQ of about 210. Now, I've spoken with him because I've been on TV programs, debates with him. So he might be possibly the smartest guy I've ever met. But if he is Penrose, then Murray Gell-Mann would definitely be second. Right? Brilliant guy. Anyway, Gell-Mann is famous for classifying the elementary particles. And he got these wonderful triangular, hexagonal patterns where each point in the pattern represented a particular elementary particle. And in one case he had a triangle with a missing apex, the top point. Like there should have been a top point representing a particle, and then 2 points below it, and then 3 below that, and 4 below that. So altogether making 10 points. Well, the row with the 4 points, the 4 particles, they were all known, and then 3, they were all known, and 2, they were all known. But the missing apex of the triangle, the 10th point, so to speak, was not known. So Gell-Mann did the same thing as Mendeleev did and predicted, oh, this missing point, there's this missing item in the pattern. And this particle, I, that's Gell-Mann, I will label omega minus, and it should have spin 3/2 and blah blah blah. He just listed the properties that he could predict from his theory, his classification theory, and invited the particle experimentalists to go away and find it, and they did. And you can imagine it was a great triumph, a wonderful triumph. The elementary particles had been classified to some extent. So wonderful stuff. Now. I'm wondering at what stage I should introduce these, the text I have in front of me. Well, perhaps I'll move on, finish this before I get down to this section, and then go to the text. All right. Well, look. So there are elementary particles with half-integer spin. There are other. Here's an elementary particle with half-integer spin, but 3/2 rather than just 1/2. There are other particles that have 0 spin, okay, and photons and some mesons. What's a meson? It's a particle of middle, like mezzanine, the mezzanine floor in the building. It's like a floor that's halfway between like the ground floor and the upper floor. So meso meaning like middle.